Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar, the CMSA at Harvard University. And today we're delighted to have Javier Gomez Serrano from Brown University, who will tell us about computers and mathematics and PV. Javier is an expert, one of the leaders in this subject, and he's worked on modular stacks and other equations, and he'll tell us how one can get rigorous results from computational methods. As I always do, I'll be watching the chat, so you can ask questions and have time for questions at the end. But if you would like to put your question in the chat, I can evaluate it and either ask you to ask it or ask it myself. That's fine as well. So with that, let's begin.
Thank you. Yeah, thanks a lot. Thanks a lot for the introduction and thanks a lot for for the invitation. It's really great to be here. So the plan for today is to talk a little bit about these interplays between computers and I will be more specific about what do I mean by computers and mathematics. Might be the one. Oops, no, but it should be something like this.
Okay, this is a good idea. If I'm not good with it, maybe it will go. Maybe it will disappear eventually. We'll give it a shot.
Yeah, if not, then we'll figure it out. It shouldn't like interfere with anything being at the top. Yeah, so I'll be more specific about what do I mean by computers and in particular about rigorous mathematics and rigorous computer-assisted proofs. So you'll see throughout the talk. And please do not hesitate to like stop me anytime, any question, anything you may have. And yeah, I wasn't sure exactly what to expect in terms of like the background of everybody here. So my plan is to start like really slow, extremely basic, and then slowly go up. Okay, so if you feel things are going too slow, just wait a little bit, and we'll get into like maybe more serious stuff. Okay, so that's sort of the plan. I wasn't also sure what to expect in terms of like the crowd. So usually when, at least let's say 10 years ago, when I was talking to mathematicians about incorporating computers into an actual proof, people were pretty skeptical. Okay, and then this was always raised. So this is why I like to start with this slide. So people were complaining, and rightfully so, that okay, the way you do your computations on your computer may influence the result, and then well, what's that, right? No, regarding, let's say, a rigorous mathematical theorem. So sadly, the answer to the first question is yes. Okay, fair enough. But still, one can still use computer system methods to prove an actual mathematically rigorous theorem. Okay, so my point is that, and this is what I'm going to be focusing today, is sort of how to use the computer to sort of prove rigorous result. And I will explain it slowly growing. And at the very end, I'll make the connection to like PDE and the problem of Navier-Stokes and other fluid equations. Okay, so that's the plan. Yes, or in terms of, let's say, you perform the same computation, the same in mathematical terms, in the same computer, you may get different results. Let's say a canonical example, and this is the example. If you do this, and you sum from 1 to 100, it gives you some number. If you sum from 100 to 1, it it gives you a different number. Yeah. Because of rounding error. Maybe not with 100, but if let's say, okay, let me be conservative here. This is definitely going to give you a different number. Okay, so from a mathematical point of view, it's always the same sum. But then how can it be, or it is not desirable that your implementation changes the result, right? So then the natural complaint is, well, we can't really trust what the computer is outputting because it is not consistent through mathematics. So even the same mathematical expression is going to give you, in floating point arithmetic is going to give you like different results. Okay, so that's the first natural complaint. And then what I'm going to propose is a way to overcome this and sort of give up on computing explicitly anything. And we're going to be bounding things. Okay, so I'll get into that. Now, again, this is also a diagram that they tend to use to explain what do I mean by a computer-assisted proof in this context of analysis and PDE. So historically, when one talks about like computer-assisted proofs, the most natural thing that comes to mind is the four-color theorem. Namely, you have an enormous amount of cases. You reduce your problem to enumerating a billion cases. The computer checks the billion cases, you're done, right? So what we have here is going to be slightly different because it is posed not in the context of a discrete problem, but in the context of a continuous problem. So what I typically will talk about is some kind of infinite dimensional problem, typically hard and infeasible by hand, that by doing some pen and paper reduction, one can reduce it to some equivalent condition of, let's say, open condition, let's say proving that something is positive, proving that some set of inequalities is satisfied, this kind of thing that maybe has, I don't know, hundreds of millions of variables. So that this will imply that. And then what we're going to do is to instruct the computer to tell us, okay, is this thing true? And then the computer may say yes, no, or I don't know. So if it says yes, then we go back and we have proof mathematical statement. If it says no, or I don't know, then we work harder. Okay, so that's the role of the computer in all these things. The computer is going to check that actually these kind of conditions are satisfied. Okay, and I will be more specific as to what do I mean by this set of conditions. But for example, think of an operator norm being smaller than 1 in order to find a fixed point of whatever we are trying to find here. For example, that would be a canonical example of an infinite dimensional problem that is reduced to one inequality in the form of an operator norm, for example. Okay, so yeah, this is all fully rigorous, and the end result is a mathematical theorem. So yeah, I mean, I've been able to, with my collaborators, I've been able to apply this sort of machinery in several contexts. And just to give a small taste of the kind of things that now we have been able to solve for like a variety of problems. So for example, we were able to study spectral geometry problems in the context of, for example, polygonal domains on the plane. This is related to the famous question of like, can one hear the shape of a drum, and sort of say things about the inverse problem. And we also use, like, for this matter, like something called the lighting method that has to do with sort of approximation of eigenfunctions of the Laplacian in like rough domains, let's say. Another application where we were successful is to use, and this is getting more into evolutionary PDEs, is to compute, for example, hard singular integrals or Taylor expansions of a solution of a PDE, and then use that to say something about the short time behavior of solutions of a PDE. And I will be more specific, and I will talk more about an example of this flavor. We were also able to use these techniques to, for example, along the lines of what I was mentioning before, bound the norm of some operator, and then use this to be a fixed point theorem to show existence of solutions, even like bad solutions, like singular solutions, ill-posed problems, that sort of like bad situations are still amenable to this kind of technique. So in the context, I mean, I wrote the word shadowing. This is coming from the dynamical systems language. This is sort of the way they phrase this sort of technique. Namely, you have an approximate solution which shadows the true solution, and you prove that close to your approximate solution, there is a true solution nearby. This is where the word shadowing is coming from. And then you sort of use the computer to fabricate the guess and prove that close to the guess, you have like a true solution nearby. And the last application, which is again moving into like infinite dimensional settings and sort of the singularity problem, is to study the spectrum of a given operator, even in the case where this operator is not self-adjoint. Okay, so then use this to track spectral gaps or to say something about the stability or instability of solutions in that context. Okay, so my plan for today is to talk of 4. Okay, so that's my plan. Okay, great. So as I said, well, let me talk about a little bit of background and these sort of things, and we'll move on. Okay, so this is something relatively new in this context. Partially, or I would say to a certain extent, because of the lack of computing. Now computing is cheap. 20 years ago, computing was expensive, and you could do finite dimensional problems, but you couldn't do infinite dimensional problems so well. So this has sort of started to take off over the last 10 years. So these are famous proofs of like computer-assisted proofs of results in analysis or PDE. But then like some of them, they require like an insane amount of effort and clever tricks and lots of compute, and they were like really massive enterprises. Whereas now these things can like very comfortably run on a laptop, no problem. Now in PDE or in fluid mechanics, which is the majority of my work, there has been work only in about the last 10 years. And these are a few names together with the groups who have been developing results and techniques in this direction. And this is definitely a growing field. And this is also kind of an invitation for people to try these sort of techniques and take a look and see whether these may help into proving like their favorite theorem. Okay. So yeah, so as I said, the plan is to say, well, I'm giving up on computing everything at this point. And instead, what I'm going to do is to propagate bounds. So at any given point on any given calculation, I will now forget what the result is. And what I'm going to track down is an upper bound on the result and a lower bound on the result. Okay, and this is what I will propagate throughout all the parsing of any mathematical expression that my program encounters. Okay, so we're going to lose, in that sense, the ability to say, well, what is this formula? I won't know it, but we will be able to at least propagate bounds, true bounds, maybe not tight bounds, but definitely truthful bounds of whatever intermediate calculation, and in particular on the final objects. And we will see that having these bounds sometimes can be enough, meaning I will be able to reduce my problem to an open condition, in the sense that I will be able to reduce the problem to saying this number is smaller than 1, as opposed to this number is 3/4, right? So then if I have room to reduce it to an open condition, then I can squeeze all my errors into the room that is left by the open condition. Okay, so that's a sort of underlying idea. We're going to work with floating point arithmetic of variable precision. I will be more specific as to when and where I use these things. And this is, for example, like the most simple example that you can think of. So we have two intervals, big X, big Y, and we have two elements on those intervals, little x and little y. And the whole point is to define this operation star over the big letters in such a way that no matter what representatives I pick, this is true. Okay, so I have the freedom to define this operation here over these two intervals to be whatever I want, as long as this condition is true. So, for example, I could, like nobody's forcing me for this thing to be tight. So I could overestimate, and it may become a problem in the future, but from the point of view of the definitions, this is perfectly legal. So if we were to think about how to add two intervals or how to subtract two intervals, then ideally, this is the kind of definition that we would come up with, right? Take the endpoints, add them, or subtract them accordingly. In practice, because of rounding error, we're going to round up the uppermost endpoint, and we're going to round down the lowermost endpoint. Yes? Because then this is going to be a lot easier for the computer to sort of, if I were to compute the accuracy at every single step of my calculation, I would truly die if I have to compute, anything beyond an academic example. So then I will sort of forget about the accuracy, let the bounds go through. If I overestimate, I'll fight that later, but I won't have to recalculate the accuracy at every single step. So I agree with you that for one simple operation, it's the same. But if I want to extrapolate and if I want to do this billions of times, then I don't want to do that calculation billions of times. Okay, so that's sort of the underlying idea behind this. And this can be very easily automatized when it comes to like implementation. You set the compiler mode to round up, you set the compiler and you calculate, you set the compiler mode to round down, and you calculate, and so on. Okay, you pay the price of a longer computation time, but that's okay. Let's assume computation time is cheap these days. Okay, so so this is sort of how things are set up in this very simple context. We can build up from here and sort of create functions defined over the intervals, for example. So before we were doing like just binary operations, we can also define functions over the intervals, and we should be worried a little bit that, okay, now the enemy of overestimation kind of pops up. F1, F2, and F3 are the same over the real numbers, but yet when defined over the intervals, they're all correct. But F1 is more correct than F3, right? So just to illustrate the fact that there is the danger of overestimating while being correct, okay? So this is something that we will have to take care of later on when it comes to like the implementation and so on. So this is more of an implementation danger rather than a mathematical issue, because all of these three are correct. The true answer is 0, 1. Okay. So we can define now functions based on like simple functions. We can define more complicated functions. Okay, we can also differentiate. I don't know here who is doing machine learning or not, but now let's say in machine learning, it's extremely popular to do automatic differentiation. So essentially what you're doing is you're going to propagate, or the way I see it, is that you're going to propagate or backpropagate not just the value of the function at any given time, but just the value, and the derivative, or a certain amount of derivatives at a given time. And then you sort of keep computing with this structure as an object, and then at any given point in time throughout the calculation, you're going to have estimates on not just the value, but also the gradients or even the Hessian and so on. Okay, as long as like f and g can be anything, they don't need to be real numbers. So as long as you have this operation plus minus defined over whatever objects f and g are, you're good to go. Okay, so my point being is that f and g need not be even intervals. They could be Taylor series in 4 variables, or some other crazy object that you can think of, and you can extend this scheme and sort of build up on, let's say, a high dimensional sort of representation of something or things like that. right? This is just a schematic way of explaining like a small building block, okay? And symbolic differentiation will not work in practice because this is too slow. And if you try to do an incremental quotient, then you're going to have like a 0/0 situation, which computers don't like. And at best, they will tell you that 0/0 is -infinity plus infinity, which is true but not helpful. Or at worst, they're going to give you a segfault. Okay, so we're going to implement differentiation via automatic differentiation. So now we know how to build functions and how to do Taylor expansions of our functions. Let's show like a simple application of these methods in the context of, let's say, zero finding. Okay, so suppose that I have a function f, and I want to find its zeros, and I want to isolate them in very small balls. For example, this is like a standard problem, right? So what I'm going to do is to use a version of Newton's method adapted to the interval setting. So I will start with some interval x, and I'm going to take the midpoint. So if I look at this operator n, what I'm trying to do is to produce a fixed point of n. Okay, so let me define n being that, and then I calculate it. So this is another interval. If it is contained in x, then great, because I have produced my fixed point. There is one and only one zero, such that f is 0 in this interval x. If I don't intersect my previous interval, then I know for a fact that there is no 0. And if I do intersect, but it's not contained, I can take the intersection and repeat again, and so on and so forth. Okay, so this is a simple application of this interval Newton's method that would, assuming infinite computation time and assuming regularity, it will track down all the zeros as long as they are simple. If the zeros have multiplicity, then one can do more sophisticated versions of this method. Okay, so just to also illustrate this in practice, this is taken from a library called ARB. And then, okay, it has like a bunch of predefined functions. Let's say we want to find the zeros of sine of x between, I don't know, 1 and 100. Okay, and it said, well, I found 31 roots, and there is no issues with not detecting roots or multiplicity and so on and so forth. And I can make it more verbose to tell me when in the program this condition 1 was satisfied. Of course, I can narrow this down a lot once I get to 1, but this is only displaying now the places where, by working with this interval 96.9 blah 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 blah, 98. Blah blah blah, condition 1 was met, and therefore the program concluded that there was one isolated 0 in that subinterval. Okay, and again, this is for sine of x, but one can do this effectively with any function. Okay, so now let me explain quickly how to integrate. So suppose now that I want to compute bounds on the value of some integral. Let's assume that f is smooth and a and b are finite. If some of this condition doesn't hold, we can still do things, but for simplicity, let me assume that at this point. So what I'm going to do is just use a classical method, integrate by using my favorite quadrature, plus an error term that usually has the form of some derivative or the function at some point where we don't have control somewhere on the interval. And then what I'm going to be doing is essentially changing this f double prime of c, which I don't know what it is, by directly evaluating on the whole interval. So this line is definitely contained on this, and this term is going to be effectively treated as an error. So at the price of enlarging a little bit the output, then I can guarantee this result falling inside here, right? So maybe this is a little bit bigger than what I need, or maybe this is a little bit bigger than the true result. But nonetheless, I can guarantee that this thing is contained here, which is what I want. I mean, I'm all for correctness, and I will fight accuracy later. Okay, so this is for like a simple integration of a smooth function. If I want to do something slightly more complicated, like a singular integral, then what I would do would be to take out the singular part. So split it into the singular part, the singularize, and the non-singular part. So the non-singular part is the same as before. And for the singular part, after the singularization, now I have a singularity of the form 0 over 0 or y over y, and I can divide by y. Okay, I can just do a Taylor expansion in the numerator, take the y, cancel out the y, and then bound the contribution from this term in this interval, and taking epsilon small enough, I can make this arbitrarily. I mean, I can take it very small. Of course, the smaller I take the epsilon, the more I will have to fight here for this term. Okay, so this is a way to do a computation of a singular integral. Okay, so yeah, so this is sort of the basic setup, and now I'm going to be moving on to, let's say, less academic examples and more like real world, let's say, problems. So I'm going to talk first about singularities for compressible oil. Okay, and this is joint work with Buckmaster, who's at NYU, and Calabora, Shi, and Stafilani, who are very close here at MIT. Calabora is a graduate student, and Gia is a postdoc, just to advertise the young people. Okay, so this is the sort of PDE that I'm interested. So this is compressible Euler. Rho is the density, U is the velocity. It is set up in R3 plus 1. Mu is either 1 or 0, depending on whether we are taking Euler or Navier-Stokes. P is the pressure. There is no divergence-free condition because the fluid is compressible. And the second equation is simply just a conservation of mass. Okay, so gamma here is a number bigger than 1, depending on like the gas, whether it is monatomic or diatomic. It has some famous values, but gamma is going to be a variable number for us. So it's a scalar taken strictly bigger than 1. Okay, so this is the kind of PDE that I'm interested in, and I want to study the blow-up problem for this equation over here. So if you look at this, and if you think about like physically, how can a compressible fluid go bad? It's sort of simple. You just squeeze it, and since it is compressible, you are allowed to squeeze it, and then you will create a shock just by pushing it somehow onto itself. So the generic blow-up behavior is a shock. A shock is where the function, the L infinity norm of the function stays finite, but then the gradient blows up in finite time. Okay, so how about other things that are not shocks? Okay, so Gooderley found a self-similar, radial, non-smooth imploding solution. So an imploding solution is a solution where the L infinity norm of the function also blows up. So not just the gradient, but the L infinity norm of the function blows up. And there was a paper published in 22, written at the end of 19, by Merl, Rafael, Rodniansky, and Scheftel. So this was a series of papers that were highly influential. They got the Bocher Prize and the Clay Award for this series of papers, where they proved that they could construct smooth, self-similar imploding solution for almost every gamma. The case gamma 5/3 was left out, and they almost every come from some complex analysis consideration where they have an analytic function, and the gammas for which they cannot do it is the set at which the analytic solution vanishes. So then it's a very small set. Okay, Anchoviasi did some numerical work on these profiles as well. And then concerning Navier-Stokes, there have been proofs of blow up for different degrees of smoothness and considerations regarding the density. Shin proved it for compactly supported density. Here, if the density is small, so if rho is 0, then it is somehow contributing for things to blow up, because if I now divide by rho, then I have dtu is equal to 1 over rho something, and then if rho is 0, then this is somehow helping the velocity to blow up. So first with a compactly supported density, then Razanova with fast decay, and then Merl, Rafael, Rodniansky, and Seftel with a slower decay. Okay, and there is another paper by Guo, Hatchikran, Zhang, and Schrecker where they use similar techniques for Euler-Poisson. So the questions that were left open before we started working on this problem was whether can you construct a smooth self-similar profile for all gamma, and can you construct imploding solutions that don't decay, so constant at infinity? And the answer to these questions is yes, and this is namely what we were able to prove in the first paper. So we can construct smooth self-similar solutions for all gamma, including 5/3. For 7/5, we construct a different family of solutions, and we can upgrade these solutions to constant density at infinity for Navier-Stokes. And there is also a follow-up paper where everything I said here was in the radial setting, and this was upgraded to the non-radial setting. So I'm going to focus mostly on the Euler part. Okay, I won't talk today about Navier-Stokes. Okay, so let's get into business. First, let's go to radial. Mu is 0, so we are dealing with Euler. And let me call alpha this number, gamma minus 1 over 2. And I'm going to consider new variables, W and Z. And these are important because the system diagonalizes. So if I rewrite the PDE in terms of these variables, W and Z, it looks like this. Okay, so it is not really important how the PDE looks like at this point. I'm going to be more specific in a slide, and then we'll see what it gives. So then if I go to self-similar, then now my PDE becomes an ODE. And now this is how the ODE looks like. It's a 2x2 system. You can even make it autonomous by reparametrizing time. So d xc w is equal to this fraction, and d xc z is equal to this fraction, right? 2x2 system, ODE, and that's it. No, how hard can this be? This is sort of like the first question that one does to himself, because I mean, after all, it's a 2D autonomous ODE. So why can't people just prove the existence of nice solutions here? And the answer is coming from the denominators. So there is a problem because this is what has to happen. Via the boundary conditions, we have to connect P naught with P infinity. And P naught starts below the red line. The red line is dz is equal to 0. So if we want to cross, I mean, topologically, we can't do anything else. We have to go, we start below, and we have to cross the red line in order to get to P infinity. Now, our only chance, if we cross at some point which is not PS, then it's not going to work, because then the denominator of the ODE is going to become infinite, and then we won't succeed. So our only hope is to cross via this regular singular point PS, which is the intersection of the numerator vanishing and the denominator vanishing. Okay, so we need to understand the behavior here close to this regular point PS, and then if we can manage to cross, then let's see later if we go to P infinity or if we come from P0. Okay, so the whole action and the whole dynamics and the heart of the difficulty lies on PS. Okay, so these are the statements of the actual theorems. We proved that for all gamma, there exists some value of R. R is the self-similar exponent, such that there exists a smooth solution going from P naught through to P infinity, passing through PS. And we can also do that for also other values of R in some asymptotic regime where n is large. Okay, so what do we do? Let's start doing some local analysis around PS. Let's Taylor expand the variables, and let's see what recurrence do we get in terms of the coefficients. So if we take a series expansion around PS, then this is the kind of recurrence that we get for the coefficients of order m. So Wm is the mth Taylor coefficient, and Zm is the mth Taylor coefficient on Z. Now, this is nice. On the right-hand side, I mean, it's a triangular system because the right-hand side will not depend on anything that has an index greater or equal than m. So if we know up to point m minus 1, we can upgrade Wm in terms of all the previous variables. And we can also upgrade Zm in terms of all the previous variables once we calculate Wm. Problems, this factor here, m minus k. K is a function of r that I didn't write, that if it is equal to an integer, then bad things happen because we're going to sort of be dividing by 0. Okay, so let's see. Okay, now this is, again, the phase portrait as we move R. So R, remember, is a free parameter having to do with a self-similar exponent. And if we are in between these numbers, R3 and R4, then if we are close to R3, we're going to come from a point hitting the line W is equal to 0. And if we are close to R4, we're going to come from a point hitting the line DZ is equal to 0. Therefore, by a shooting method or by continuity, there exists at least one value of R that came from P0. Okay, so that's one ingredient. The other ingredient is that for any value between R3 and R4, our solution from PS is going to go to P infinity, and it's not going to come back to the line DZ is equal to 0. Okay, so now what we have to do is essentially prove these conditions A, B, and 2. Okay, so this is our plan in order to prove the existence of smooth solutions. Okay, let's see. We're going to use a barrier argument. So we're going to, the first thing that we tried was to construct a global barrier and then show that the field points in the right direction, so it cannot cross the barrier. Now we tried pretty hard and we didn't succeed because it was like too complicated or it just didn't work. So what we ended up settling for was a combination of a global barrier and a local barrier. So the global barrier has this nice property that everywhere the field points in the direction that it has to point, but the solution starts going away from the global barrier. It does enter eventually, but to start with, the solution doesn't start below the global barrier. So what we do is to correct with a local barrier, which is good up to some time, and then the field points in the other direction. And we make sure that the local barrier intersects the global barrier before it goes wrong. So in that way, we can sandwich the solution between the local and the global barrier. Okay, so this is what is going to be the setup. And now you can already see where the computer is going to come in handy, because what is this condition at the end of the day? Well, if you give me the global barrier parameterized by whatever, then all I have to check is that the component of the field in the direction in the half plane given by the whatever barrier is strictly positive or strictly negative. So we have reduced the problem of finding the singularity into checking that the field across all of these barriers points in the right way. Okay, so this is an example. This is one barrier parameterized by BW and BZ. And then we can write down the barrier in implicit form using this resultant. And then what we have to check is that this polynomial given by this 4x4 determinant substituted along the barrier is negative for small s. S is the variable that parameterizes the barrier, and positive at some point for all everything holding for all r. So these amounts, like the B3 is a polynomial of degree 3. When I substitute, and so is the B3W and B3C, when I substitute into the resultant and divide by the trivial cancellations, this gives me a polynomial of degree 6 with coefficients that depend on 2 parameters. So what I need to do, and this is what I instruct the computer to do, is to tell me, well, my degree 6 polynomial that has coefficients on 2 variables has a sign. And then I do just branch and bound on all of this, wait a little bit, and then the computer says yes. So this is one place where we use the computer to do the job for us. And there are other instances, but this is an example. Let me give another example in this regime. We can also say some of these conditions on the barriers, they can be substituted by some sign and some lower bound sign of the coefficients and some lower bound of the coefficients. So the problem is that if we look at the recurrence, this recurrence is effectively super exponential. So the coefficients are sort of big and difficult to track. So if we have a big index, we can do induction. So we ask the computer to check this sign condition and this lower bound on the coefficients condition for the first 10,000 steps. We say, well, compute these 10,000 coefficients of our Taylor expansion, check whether this is correct, and then we'll handle the rest and take it from there. Okay, so this is also something that we ask the computer to do. And this is what the computer told us. And there is no typo in the slide. So this is truly the magnitude of these coefficients. So the computer did this calculation, and some of the coefficients are of this size. So 10 to the 44,000 and change, plus minus an error, 10 to the 44,000 and less change. Okay, so we really had to fight here with high precision throughout the computation, but nonetheless, we managed to get 20, 30 digits correct, and that was enough to extract the sign of these things. Okay, so this is one example where we did use a computer to prove a theorem. You may argue that, well, this is finite dimensional, it is a polynomial in one variable. How about infinite dimensional problem? Okay, so let me talk a little bit about infinite dimensional problems. I'm going to talk about something called the SQG equation. It is not too important what this is, but just to fix ideas and to illustrate where does it come from. So it is this transport equation. Theta is a scalar. This is in 2D in space, 1 in time. U is an incompressible velocity, and U is given by this singular integral operator via the Riesz transform. So you can also use the fractional Laplacian or write it in Fourier and get a multiplier for U, or the Fourier transform of U as a function of the Fourier transform of theta. So this is an equation coming from geophysics. Geophysicists were using it via numerical simulation to understand the lower layers of the atmosphere. It also has connections to oceanic currents. But there is also some mathematical analogy with 3D Euler. So there is a structure in terms of theta versus the vorticity for 3D Euler. So people drew this analogy and thought that, well, maybe if we understand this problem, which is 2D, we can understand 3D Euler better, which is 3D and seems hard. Now, the sad reality is that even this problem is still open, whether there is a finite time blow up or there is global existence. Okay, so even though this is in principle simpler because it's one dimension less, it's still not well understood. Okay, so what did we do? Well, what we did was to construct solutions, was to construct the first solution, non-trivial, which was global. So we constructed actually a family of solutions that were global in time and had finite energy. So the way we did it was to take a radial function. So a radial function is always a stationary solution because of the way the equation is set up. And then what we did was to perturb it and use bifurcation theory and perturb it in a correct way, in a way that what we got was a rotating solution. So we had a solution that its only behavior was to do some rigid rotation movement on the plane. Okay, this is all, and therefore it exists globally because it doesn't really change the shape on the rotating frame. Okay, so we are going to do that using bifurcation argument. And in order to do that, we need to find an eigenvalue problem, right? So, so after a long calculation, what we have to do is to solve the following eigenvalue problem. B is a function, is an unknown. Lambda is the eigenvalue, which is also an unknown. I is an explicit function that has to do with elliptic integrals. And T is an operator that also has to do with elliptic integrals. So we have this sort of eigenvalue problem where part of the left-hand side is multiplication and then some nasty operator here, which is not even self-adjoint. So we can't apply maybe more heavy machinery about self-adjoint operators. Okay, so in particular, lambda has to be real, but we have no guarantee that this is even the case. Okay, so what are we going to do? Well, we're going to take the symmetric part. We're going to take the symmetric problem, find it, solve it numerically in an approximate way. So it will solve BSJ is an approximation for the symmetric problem. Lambda star is an approximation for the symmetric problem. E is the error coming from our numerics. And then what we're going to look for is a solution of the type the guess plus some perturbation in the orthogonal complement of the guess. Okay, so now what we have to do is to solve for V. We expect V to be small. Okay, so this is essentially what sort of another point of view of this problem. We have the eigenvalues of the symmetric operator, lambda star, C star, and then the antisymmetric part is small. So then when we look at the full operator, it is a perturbation of the symmetric part. And therefore, there is one eigenvalue somewhere here, and we can bound the rest of the eigenvalues somewhere in this ball or further to the right. The point is that in this ball, there is one and only one. So therefore, it has to be real, because if it were complex, then there would be its imaginary, it's a complex conjugate, and therefore there would be two eigenvalues in that ball. So contradiction. This essentially forces whatever eigenvalue that is here to be real. So the important magnitudes are the relative size of the radii of this ball and this ball versus the spectral gap between the first eigenvalue and the second eigenvalue. Okay, so we need to somehow make sure and quantify that this distance here is bigger than the sum of these two distances. So in particular, we need a lower bound on C star. Now, finding upper bounds of eigenvalues is easy because you can do like Rayleigh-Ritz methods or maybe other techniques. But finding lower bounds is not so easy. So let me explain how to find a lower bound of the second eigenvalue of that horrible operator, right? So we want to find the bound from below for this operator here in the space of orthogonal complements to BSJ. So let's drop first the multiplication part. Here we're going to just give up on anything coming from here. We take the minimum, and what we want to understand is the compact operator. So we want to understand the eigenvalues of T tilde V against V. Now the point is that T is compact. So then we're going to reduce this calculation here on an infinite dimensional space by a finite dimensional calculation. And due to the compactness, we're going to be fine, because then we're going to be able to approximate our infinite dimensional operator by a finite rank 1 modulo some errors, right? So if we take this Tn, which is the projection of T acting on the projection of V's, now this is a matrix, and therefore we want to understand the eigenvalues of a finite dimensional, potentially very big matrix, and then some error term that I'm going to throw away. Okay, so how to understand the eigenvalues of a finite dimensional matrix? We can use Gauss-Gorin's theorem, for example, and then if the matrix is diagonally dominant, or if the matrix has entries that are far from the part of the spectrum that we're interested, then we can just ignore those, right? So Di are the Gauss-Gorin's disks, and this tells us that the spectrum is located in the union of these Di's. So then, as long as we can like approximate very well the ones that are meaningful, the ones that are close to the C star, then the rest we can just do. We can just get away with a reasonably good job. Okay, so this is going to take take care of this part. Now, how to deal with that part? How to deal with the error part? Well, the error part turns out that it's an integral kernel. Again, it is the difference between the nasty thing with the elliptic integral minus the even nastier thing with the projections. So we can just stack everything together and write it in the form of a kernel, and then the norm of this term here can be bounded using generalized Young's inequality and reduced to some integral in rho and some L infinity norm in rho prime and the opposite. So it is reduced to an integral with one parameter and two of these. Okay, so now I explained before how to compute, and this is a singular integral because the elliptic function has a logarithmic singularity. So K is explicit but not easy. It involves elliptic integrals, and K is singular. It's a logarithm, so it's integrable. But we need to do sort of a similar adaptation of what I explained before for the Hilbert transform, but this time in 2D. We need to kind of subtract the singularity, get the smooth part, integrate the smooth part, and then deal with the singularity by hand. Okay, so this is sort of a more serious problem, and then the numerology goes well, and we can bound this thing, and we can produce a gap between lambda star and C star that accommodates for the other little balls around lambda star and C star, and we win. Okay, so in more realistic settings, and in particular in what I will talk in like 2 slides, we may not have the luxury of having our operator to be of the form identity plus K or multiplication by K, but we can usually split it into something that we understand very well, or we can even compute things explicitly plus a relatively compact term. And then this is a perturbation of that. We can approximate it by a finite rank, and then relative to that or precondition by S inverse. And then if we look at S inverse KR, then it is compact, and we can do sort of a similar trick. Okay, so that would be a more realistic setup. Okay, now, okay, so there was something promised about the singularity problem and fluids and so on. And I also promised that I wouldn't talk too much about machine learning. So just one slide. We have been, together with Wang, Lai, and Buckmaster, we have been successful lately solving approximately self-similar solutions of PDE using machine learning techniques. So this is an image from our paper. It is taken from Boussinesq. So this is what the ML predicts as a self-similar solution. The errors are pretty small relative to the data, and we are confident that this is like a good solution and so on. This was the first self-similar solution computed for Boussinesq with a boundary. Okay, now the plan is to sort of using this paradigm plus the previous computer-assisted techniques to find and prove blow-up for incompressible fluid equations. So this is sort of a program that we are currently working on, and this is kind of how the proof would look like. So first, find a suitable approximate solution, self-similar approximate solution that can be found by machine learning, but it could be found by any other techniques. But we are definitely lately being more optimistic about the success of using ML to solving step 1. Then look at the linearization around the approximate solution and split it again into some finite dimensional part plus a tail plus an operator that we understand very well, and it is dominant in the same spirit of what I just commented. Then show stability of that operator. So essentially, again, track the spectrum and sort of prove that modulo a finite number of directions, all the spectrum is contained on the left half plane. We can handle some amount of instability using topological techniques from this paper. Now, one thing is that all of this goes through also for a sufficiently small viscosity. So one can add viscosity to the problem at a scale which is slower than the blow up scale, and the whole proof will go through. Then do 1, 2, 3, and 4 rigorously using the interval arithmetic framework that I just described, and lastly, upgrade the linear stability into nonlinear stability. So that way you can sort of fabricate a trapping region where you have your guess, but then the field is pointing in, you never escape, and all of this ball blows up when lifted to xt coordinates. So then you know that at some time you will blow up in finite time. Yeah, and the point is that, well, in any of these steps, I ever used anything about the equation. So this is really agnostic to the PDE itself. I mean, of course, provided that there is an actual solution. If there is no solution, then there is nothing we can do. But as long as there is a solution, this is a strategy that could potentially work and is quite agnostic to the PDE. And I mean, we've seen that for somehow the ML part, the ML finding of the approximate solution, that was also quite agnostic to the PDE as well. And we were successful in finding self-similar solutions, not just for Boussinesq, which is the one that I showed, but for a few other PDEs that were new. So again, let me stop here. Thank you so much. Thanks a lot for the attention.
Thanks. Great talk. Questions from here, the online audience.
Well, but step 5 refers to 4, 3, 2, and 1, or 4, 3, and 2. So bound everything rigorously refers to like do the decomposition and prove the estimates rigorously. So step 5 really, okay, 4 is a remark, but this has to be done rigorously, and this is coming from this decomposition. So step 5 is referring to step 3.
Step 6, is there any way the computer?
Yeah, the computer helps. This is a combination of pen and paper and computer-assisted proof techniques. So you have to estimate the nonlinearity, but the nonlinearity is typically going to be very small. You are doing the stability, like this ball is medium-sized, is, let's say, of epsilon. Now, what you're truly estimating when you estimate these terms, so there is one good thing and one bad thing about this. The good thing is that all of those terms are epsilon squared. So you can be pretty generous with your estimates, meaning that you can do bad bounds. The bad thing is that there are many, or there could be potentially many. And you have to compute them all. So now going back to your question, if you really need to do a good bound here, you can use the computer. For practical purposes, it is a lot faster to do a bad bound and estimate it by hand. But if things are tight and you're struggling with the numbers for, let's say, even 1 or 2 of these nonlinear terms, you can definitely upgrade your bad bounds into good bounds and then use the computer to produce much better estimates of those bounds. Which? Yeah. I mean, in that sense, yes. But the nonlinear stability, again, this is nonlinear around the approximate solution, not nonlinear around 0. So then the nonlinear stability is annoying, but usually goes through, because you're estimating things that are fairly small, and then, okay, you may cook a very nasty PDE that makes your life hard, but in general, out of all of these steps, this is not the hardest. I mean, it may be the most time-consuming, but technically, this is not the hardest. The hardest one is really showing the stability and then bounding the transient growth of the evolution of solutions close to the guess. So the hardest part here is the linear part, not so much the nonlinear part. So you have something like BTU is equal to LU plus NU. So if you know that this thing, let's say you do energy estimates. So you right. So now this is 1/2 d by dt. Let's do L2. So suppose now that you are on the stable region. So now this is bounded by something like this. This one. But now this is morally like the integral of u cubed. But remember, u is in a small ball. So then you could do, I don't know, L infinity, for example, here. So you could, for example, do something like this. And then this is already gaining u and epsilon. So then you can absorb this into that. Okay, so I mean, of course, this is a sketch, and it may depend on the particular PDE, but morally, the nonlinearity is not super dangerous. It is counterintuitive because you are maybe more used to the PDEs being linearized around 0, and then the nonlinearity does play a role. Like if you were to think about like Euler or Navier-Stokes, then of course the u grad u is dangerous. But once you linearize around your approximate solution, dangerous part is the linear part, not the quadratic part, because the quadratic part, assuming all the estimates sort of go through, is going to stay very small. Like if you don't leave this ball, this is not going to matter too much.
More questions from the online audience, or let me ask. Suppose one wanted to apply this to one's own PDE. So I mean, I presume this is not something that you can effectively just do in Mathematica. You've combined a number of software packages.
I don't know.
So
I wish.
Do you have at least like examples like Jupyter Notebooks or something where you work something systematically so somebody could see all the techniques and the packages and the rest?
This is, well, first of all, the package is written in C. So there is no Jupyter Notebook.
But it's really specifically C for your specific equation, or it's a general thing?
The underlying package that handles the interval arithmetic computations. Okay, there is a wrapper into Python and other languages,
Right.
but it's not as well developed as the basic package, which is written in C. So this handles, let's say, the basic operations, even addition or whatever. And then on top of that, we have had, I mean, over the years, we have developed our own library throughout completing smaller projects, but there is no standard package that, singular integral or things like that, let alone Boussinesque or PDE blow up.
Okay, so
it's more like an ad hoc calculation for every problem.
Right.
However, when it comes to the actual papers, the code is submitted along with the proof. So anybody can download, and there are instructions, like careful instructions as to how to run it and how to compile and so on. So you can mess around with the code. This is made available, but it's more of a specific for each project.
Right.
We do reuse many parts, like we only need to know how to integrate once, for example.
Right.
So the integrators are reused, but then the specific things or the specific functionals or energy estimates or whatever, they are more on a equation by equation basis when it comes to the code.
Right. So there's maybe an opportunity for somebody somewhere to write like the TensorFlow or package for doing this general class.
Of course.
Right.
No,
Okay.
definitely.
Right.
definitely. Yeah, this software developing is difficult because
Yeah, of
there
course.
is very
It's
little reward.
It's a different thing than mathematics, obviously.
Right.
Yeah.
So then it's difficult to find libraries that are like well maintained and so on.
Okay. More
Yeah,
questions,
a question. Yeah,
from the audience or,
yeah. So a
not,
question.
seeing any? So in that case, let's thank Javier for a very impressive, work and, talk describing it. And, so there will be, no talk, next week, and in 2 weeks, we will have, Gabriel Gand from MIT, and he will talk about, Lilo, a system for, generating, software packages and automatically solving, programming problems. So I look forward to seeing you there. Bye.